Hello. Hello. Yeah, so it's great to be able to talk here, and I kind of apologize because my talk is going to be elementary. But on the other hand, the students, everyone is going to understand it, so you can ask a lot of questions. Okay. So ZMC, by ZMC, I mean zero mean curvature. So that, of course, minimal surfaces in R3. By that, I mean minimal surfaces in R3, maximal surfaces in L3. L3 is Lorenz-Minkowski space, you know. Also Born-Infeld solitons, which can also be thought of as ZMC, time-like minimal surfaces, and so on. Okay. And by CMC, you know, you have seen a lot of talks on constant mean curvature surfaces. So these also can be thought of in both in Euclidean and Lorentzian setting. Okay. So what is the interpolation problem? There are many versions of this, but the one I am going to look at today is like if you have two curves which are real analytic. First problem is going to be in L3. L3 is, by the way, ds squared is dx squared plus dy squared minus dz squared. Okay, this is the Lorentzian R3 equipped with this metric. So so there are two real analytic curves. How close should they be so that there is a ZMC or a CMC surface between them? That is my question. Okay, how close? And this is a version of what is known as the Plato's problem. It was solved by Douglas, and Douglas in the case of minimal surfaces in R3. Okay, so yeah, the exact statement about how close they should be is there. So, and it is to do with the area. So basically, if the area, the curves should be close enough so that the intermediate area should be less than the area spanned by the sum of the area spanned by the graph. Okay, which is very natural, and this was proved long time ago, 1930s, by Jesse Douglas. So now, so in EN also he showed this result. Now Vekua uses implicit function theorem for Banach spaces in order to solve the Plato's problem for all curves which lie sufficiently close to a given plane in E3. And Hamilton solves the Plato's problem for minimal surfaces when the graph is when the minimal surface is a graph using Nash-Moser inverse function theorem. And the problem of interpolating curves by maximal surfaces for specific examples has been considered by Fujimori, Rossmann, Umehara, Ouyang, and Yamada. So the existence of space-like constant mean curvature surfaces spanning two circular contours have been considered by Lopez. Again, specific examples. And Plato's problem for maximal surfaces has been considered, for instance, in this you saw, I think, a lot, the maximal surface or CMC surfaces in pseudo-hyperbolic spaces. You saw these, lot of these examples. And this work was done by Labori, Tullis, and Wolf, where the boundary data is at infinity. And so coming back to our problem, so we have done for maximal and minimal surfaces to begin with, and then Born-Infeld solitons and so on. So, in one of the problems which I'm going to talk about today, we have a space-like closed curve and a point, and we want this point to be a singularity, and we want to know what kind of curves are allowed so that there is a maximal surface between them. So we got some conditions, sufficient condition. And so the interpolation between two curves, so this is another set, interpolation between two curves by maximal and minimal surfaces. So this was done together with Rahul. But of course, Pradeep helped a lot with formulation, everything. He helped a lot, but for some reason he couldn't, he was very busy and he couldn't remain in the project. So we use, so basically we use the inverse function theorem for Banach spaces to interpolate a given analytic space-like curve A in Lorentz-Minkowski L3 space to another real analytic space-like curve, which is close enough. So we'll today talk about how close they should be in a certain sense by constructing a maximal surface containing them. Next, we apply the same method to interpolate two given real analytic curves A and C with minimal surface. And it is actually, we do it by, there is the Bioling problem and a short solution to it. So there's a formula and we just want to invert it. So that's why inverse function theorem played this role. So the Bioling problem and its short solution play a pivotal role. And next is the one I was talking about. So there is a point which is in space in L3, which is which we want to be a special singularity. And there's another curve. These two things are given. How close should they be? Or what is the condition on the closed real analytic curve? It's also a null curve such that there is a maximal surface between them. And then CMC surfaces, I won't talk too much about this. This is joint work with some of my students and postdocs. So again, it's possible to invert the Sim-Bobenko formula and show existence of a CMC interpolating between two close by curves. We have found the neighborhood so that this happens. So this is one type of problem I'm going to talk about, just touch upon. I won't go into the proofs very much. But the other set of problem is, supposing you have some minimal surfaces, say a row of helicoids you've placed in a plane or in a line along a line, and you want to know, is there a minimal surface which interpolates them, which contains all of them? You know, in the sense that the height function of the minimal surface splits into summation hi xi, where these are also minimal surfaces. Could be infinite sum. But this is very hard to get. So we have also relaxed the problem to consider the case when these HIs are not really minimal surfaces, but they are scaled or translated versions of minimal surfaces. Okay. So this was, of course, motivated by a physics problem where, you know, what do they call it? Screw dislocation in crystals. So the defects, they are like helicoids. And on the other hand, the whole surface is like a shark surface. Okay. So I unfortunately don't have the pictures, but if you look up shark surface, type 1, type 2, you will see that there you can see the helicoids almost. Okay. But here we are interested also in decomposing the height function. So it was known that a given array of helicoids, one can interpolate them by a shark's minimal surface, example from crystallography, Randy Camion and his group. And there are other examples like this. We can also use Euler-Ramanujan identities sometimes. Sometimes we are lucky we can get this kind of structure. And then Weierstrass-Enneper representation and other techniques depending on the application. These techniques carry over easily to maximal surfaces, Born-Infeld solitons. I told you Born-Infeld solitons are also can be thought of as ZMC in a certain sense on time-like planes. So Born-Infeld solitons and time-like minimal surfaces. And recently, Rahul and his collaborators, students, Shubham, Priyank, and Siddharth have explored this and got many more results. So, so as you know, the minimal surface equation for a graph, when it can be locally written as a graph, is this. And you can see it's highly nonlinear, so how can you even add the, it doesn't make sense to add the height functions. But on the other hand, in isothermal parameter, it just becomes harmonicity of the coordinates. But the nonlinearity is in the isothermal parameterization, right? So now the general solution is given by the Weierstrass-Enneper representation, which you saw in many of the talks. And for in Lorentz-Minkowski space, this is the maximal surface equation, and we want it to be space-like. And so this is the mean curvature equation in Lorentz-Minkowski space, and they again have Weierstrass-Enneper representation. But generalized maximal surfaces can now have singularities because there is a negative sign here. So we can have singularities, conical, cospedal, swallowtail, and so on. So I have some pictures finally. Space-like elliptic catenoid, this looks like this. So sorry, these images were just publicly available. I'm not good at generating pictures. So these I just took from the internet. So this is space-like parabolic catenoid and space-like hyperbolic catenoid. Okay, for example, you can see there are singularities. So, let's do the interpolation of two curves by maximal and minimal surfaces. So just maximal surfaces. No, right now I won't talk about the other one. So what is the Bioling problem? The Bioling problem is also very pretty. So you have a real analytic curve, and you have a real analytic distribution for the normal, the candidate for the A to the surface. The curve is supposed to lie on a surface, and this n, this normal field is supposed to be normal to the surface along the curve. Okay, these two conditions are given. Then Bioling asked the question, is there a strip, a maximal or a minimal strip? Minimal strip. He did it in the case of minimal surfaces. So is there a minimal strip which contains this curve, and as I said, the normal distribution is along this. And they gave a beautiful formula for it. And we have the same thing along same. We have the similar formula in the case of maximal surfaces. In minimal surfaces, this is a minus sign and a maximal. So let me just read it quickly. So L3, L3 and A is a real analytic space-like curve with A prime not equals to 0, and it can be extended to a little domain. So the domain is like this. I is going to the curve, and there's a small little domain omega. Okay, and containing the I. I is the say 0, 1. So now you take time-like unit normal, so that will have this, and this is a distribution which you fix a priori, and A is also fixed. Now you should be able to write the formula for the maximal surface. And it is unique as long as you stay near the I. And as long as NW and AW have complex analytic extension, you will have uniqueness. Sorry, this should be A of T. So this is the picture. So now our idea is, now I have another curve close by. I want to change this normal distribution such that this strip actually covers this curve also. Very simple. Just change the normal distribution in some Banach space. Okay. So that this strip actually can be continued to the other curve. So these two, A was my given curve, and now supposing C is another curve, or L, let me call it L. L is another curve. How close should they be such that this Bioling problem, this Bioling solution actually extends? So what N we should take, and what should be, how should we extend it so that it contains the other, what N should we take? So that is the simple this thing. And yeah, so you saw that the Bioling problem can be written as A plus I, I'm calling this D, this whole thing integral, right? So basically we have to actually invert this kind of thing, but we have to also allow for a conformal map from the domain to the domain. A plus ID plus compose with gamma. And it's not easy to invert this. So you have to actually shrink the space parameterize it by the unit normals, and so I'm not going into all the details. But ultimately, finally, so if I have time later, I'll go into the details. But ultimately, this inversion can be done, and local inversion, like I calculate DH of that map and restrict it to certain subsets of the Banach spaces, and then I invert it and then try to show that actually on the whole space it inverts, and there is the so the Bjorling-Schwarz function is invertible in suitable domains. And so now, what is that suitable domain? You have inverse function theorem doesn't hold on a big domain, right? It has to, so that will translate into a domain for how close these curves should be, right? So, so L of, so let's write this. Let's write the domain, the neighborhood at least. So how close A and L should be, such that there is this Bjorling formula between them. So, so L from I to L3 has a differentiable extension from omega bar to C3, analytic on omega. We denote the extended function by L again, and the space of extensions by the same thing. SP is such that C belongs to IL3, C prime is greater than 0 on I. And this is such that real C prime du is space-like and non-zero. So, okay, I don't know why I got this. Right now, I don't need that. So, A and D0. So, I have fixed a D0. That is another thing. D0 is a fixed quantity. Around that neighborhood, I'm going to find a maximal surface. So, A plus I D0 is my fixed point to start the inverse function theorem, right? So, A prime L equals to this. So, this is A plus I D0 is what is called L isotropic. That means this is the conformality condition, right? And then we show, well, I am not going to explain all this, but let me just go directly to the neighborhood. So we construct DLZ to be A primed L. This is cross product in the Lorentzian space. A prime cross L prime cross L prime mod by A prime cross L prime dW. So this is my DL. That is that part. And so omega be a disk in C. A D0 belongs to SP fixed such that this is L isotropic, and X real part of A plus I0 is a generalized maximal immersion in L3. Then there are eta 1 and eta 2 greater than 0, such that for all curves in SP, such that L minus A in the sup norm is less than eta 1, and L prime minus A prime. So you have to actually go close to not only A, L prime also be close to A prime. And DL also must be less than D0. I mean, in the neighborhood of D0. So this also less than eta 2. And DL prime is also in the neighborhood of D0 prime. So you can construct this delta T such that there exists a generalized maximal surface. And so L of U is X U comma 0. When along this line is L of U, so I have reversed this. Along this line is L of U, and X composed gamma inverse. So there is a gamma such that X composed with gamma inverse is A of U. So basically, we get that this X interpolates between L of U and A of U. Okay, so that is just a little very simple and analogous to that minimal surfaces. So here only difference is actually it's easier. Minimal surfaces is easier because you need to take only Euclidean cross product. Over there in this problem, you needed both. Sometimes you needed the L cross product, sometimes you needed the E cross product. So this was easier. Okay. So now what is here, again, I'm not going to talk much about this, but you know for CMC surfaces, there's the Sim-Bobenko formula, and it can be inverted using the inverse function theorem. So again, two curves which are close by, is there a Sim-Bobenko formula like interpolating them? And we found a neighborhood such that the two curves are close enough, then there is such a thing. And so now for some concrete examples. So this is another thing which we did, Pradeep, Rahul, and myself. So there is so this is we will just do maximal surface case. Minimal surface again can be done similarly, but in this case we are interested in the maximal surface case because we want the curve, one of a given curve to be null and a special singularity to be a singularity. For example, for elliptic catenoid, there is a conical singularity, right? So there is a little different way of writing the maximal surface. So you write f as u comma v comma w omega 2 L3. So combine the first two as u plus iv, call it h. H is u plus iv, and w is the height function. Such that hz bar bar minus wz squared equals to 0. This is the condition of the conformality. And I have not written, I guess, the minimal surface equation. Yeah, of course I have written it. Hzz bar is 0 and wzz bar, sorry, maximal surface means hzz bar is 0 and wzz bar is 0. And this is equal to 0. This is the conformity condition. And if this is not, this is identically 1 will correspond to a singularity. So this is not identically 1. Sorry, this is equal to 1 will correspond to a singularity. We don't want the whole thing to be a singular thing, right? So it's not identically 1. So generalized maximal surface is the equivalence class of maps F, where the relation is a change of conformal parameter. For example, elliptic catenoid. Elliptic catenoid, H is what? Half Z minus 1 over Z. WZ is log ZZ bar. And F of Z is H of Z WZ, which is given by these. And then this condition is 0, you can check. And this is also equal to 0. But on mod Z equals to 1, HZ, mod HZ is equal to mod HZ bar. So the whole unit circle goes to that point in the elliptic catenoid. So the elliptic catenoid, right? So the whole unit circle, mod Z equals to 1, goes to that. So that is the singular set. Any questions? This example is clear? So then there are non-examples, of course. So yeah, so what is the singularity set? As we said, singularity set is where mod hz minus mod hz bar is 0. And a special singularity is when mod z is equal to r goes to a point, right? And points where mod hz is not equal to mod hz bar holds at, these are called regular points. And at these points, f will be an immersion. And if f is not an immersion, then in particular, this is 0, which will mean mod hz is equal to mod hz bar. And this is a generalized minimal surface. Then this corresponds to the singular set. That is what I was referring to. But one very nice way of writing it is also this, because as you see, in the conformality condition became this, hz bar minus wz squared is 0. So in that case, this f of z is given by this. So the w can be replaced by in terms of h, and it can be written like this. So once again, one can do the elliptic catenoid. So what is the singular Bioling problem? The singular Bioling problem is when you have a curve, z is rho e to the I theta you put. So you combine it, the h part is gamma 1 plus I gamma 2 e to the I theta, and gamma 3 is the height. L is also like this. And gamma primed L, this is L inner product, I'm sorry. This is L inner product, this is equal to 0. And gamma is a null real analytic closed curve. L is a null real analytic vector field. And at least one of them is not identically 0. Gamma and L are both defined over S1. The above data is known as singular Ouyang data, and name is given by Kim and Young. They studied the singular Ouyang problem in detail and they actually found solution. What is the solution we want? The solution we want is f of e theta is gamma e theta, f of e to the I theta is gamma of e to the I theta, and del f del rho at e to the I theta is L. L and gamma are prescribed and they should satisfy this. So, okay. So, we have also given the existence theorem for, we gave a little slightly different proof from there because it will be more relevant to our needs. So, in the HW notation, we try to write everything. So, we gave a solution that given a real analytic null closed curve gamma from S1 to L3 and a null vector field L, such that this is 0 and they do not vanish identically. If mod Gz, that is the real analytic extension of the Gauss map, is not identically equal to 1, then there exists a unique generalized maximal surface defined on some annulus, such that e to the I theta goes here. Del f del rho e to the I theta at e to the I theta goes here with the singular set at least mod z equals to 1. So basically, this set, this entire thing is a point. So gamma theta is CC, entire thing is a singular curve. And we are interested in the case when gamma theta is a constant because we want it to go to a point. And again, elliptic catenoid case, we have an example. So the main question is the following. Given a real analytic curve gamma theta, does there exist an f and a generalized maximal surface and an R naught such that R naught e to the I theta maps to gamma theta and f has a special singularity at mod z equals to 1. So basically this problem. I have an arbitrary curve gamma. Is it arbitrary? We have to find what is the condition on gamma, and there's a point P here such that the mod z is equal to 1 was there, and this is a null curve. So we do modified Fourier constants of f and g. So I first write, sorry, where is gamma? Gamma I write as, oh, I have not written that. Here, gamma of R naught e to the I theta is f and g. I write it like this. And then I write the modified Fourier coefficients. So C is this constant, and then I take e to the minus I n theta, integrate these, and there are these. So these are like, we are calling them modified Fourier constants, Fourier coefficients of gamma, and real analytics. So the series will converge, and so yeah, Hz and Wz are given like this. So in that term, and the condition on gamma is if gamma 1 theta be a closed real analytic space-like curve, then there exists an S naught not equal to 1 and a generalized maximal surface such that S naught e to the I theta goes to gamma 1 and has a special singularity if and only if there exists an R naught not equal to 1 and these constants such that gamma of R naught e to the I theta is gamma 1, where f and g are that way. Their Fourier coefficients are these, and the Fourier coefficients must be related like in this complicated manner. So this is, the proof is using singular Ouyang problem. Okay, and if you take gamma 1 is this, and R naught is half, Cns and Dns are 0, only C1 is half, D1 is 1, you get the example of elliptic catenoid. So you can take various coefficients like this and try to construct many examples this way. These are very natural conditions actually, because it's an if and only if question. So, and you can construct many examples by choosing your Cns and Dns appropriately. Okay, any questions? Now I will go for the next topic. So the next topic is interpolation by minimal surfaces. There is a Euler-Ramanujan formula, tan inverse tan h y cot x is equal to summation k goes from minus infinity to infinity tan inverse y by x plus k by. Okay, and the left hand side is height function of a Shark's first surface, right hand side is height function of shifted helicoids. They are all minimal surfaces. So, right, so you have an array of these helicoids and you sum them up, the height functions, and you get this. So this is first, probably not first time, but it is circulating in the condensed matter physics, crystallography, they use this, where these become the defects. So Randall Canyon of UPenn and his group, I saw their paper, and I met him and he explained this to me. And so we do, there are sometimes accidentally you have this a lot, or I mean, you can do this again. So for example, z of xy ln cosine y by cosine x, that's again height function of a Shark's second minimal surface. And I claim that actually you can do a finite sum with shifting, okay, scaling x and translating. So again, Euler-Ramanujan identity, cosine of x plus a by cosine a is this, right? And we take ln on both sides. Well, the sum has to converge. You have to see that this sum converges. And then, so z of xy is this. So we can turn it into a finite sum. How do we turn it into a finite sum? So we write this equation, simplify it. So this was joint work with Kohinoor Ghosh and Soundarajan and yeah, and myself. So they were MSc, one was a PhD, very early PhD student, and one was, Soundarajan was an MSc student. So this is perfect for an MSc project. So this is summation, so k equals to 1 to infinity, I have this. And so it's an infinite sum, but I can turn it cleverly. So I write this as f ln of f and g, okay? And then I write, divide k by n and write k as np plus m. So the infinity is now transferred to p, and n is some fixed number, np plus m. M is the remainder which can go from 0 to n minus 1. Okay. And when I write, so I rewrite it like this, and I notice that c n minus 1 minus m is minus cm. And then one can also argue, because of Ramanujan's identity, Euler-Ramanujan identity, you can actually interchange the infinite sum and the finite sum. Once you interchange, you get this very easily. So I get it in this side, and that becomes this. Summation n goes to n minus. Okay. So that is interchanged with. So now there are some other decompositions possible. So that was a beautiful one because, well, in a sense, you can actually see it also. Like you can put it in Mathematica and see the surfaces converging to that one. So we actually did all that. So there are other techniques to get some decompositions. So you know that there's the, near non-umbilical points, the Weierstrass-Enneper representation of a minimal surface looks like this, where R is a non-vanishing meromorphic function, but it's holomorphic on omega. R, you pick your favorite R and it will pop out a minimal surface. Okay. So now what we can do is, we can divide my R into R1 plus R2 plus Rn, right? Because it's linear in R, I can just do that. And then what I get is, for each I, so R1 plus R2 plus Rn equals to R. So for each I do xi, yi, zi, x naught by n, y naught by n, z naught by n, plus all these terms. And then what I do is, so easy to see that z of zeta 1 plus zeta 2 is sum of these. So in zeta 1, zeta 2 coordinates, actually this is sum of the z coordinates. But it's not really the height function. So we have to solve zeta in the domain where you can solve, like what I'm trying to say is, for each I, zeta 1, zeta 2, if you can solve in terms of xi, yi, and go interchangeably, then z of zeta 1, zeta 2, you can write as z of capital Z of xi, yi. Right? So that's what we can do. So, and then I want to write xi, yi in terms of my xy. So again, through via the zeta 1, zeta 2, I can find the change of coordinate, which gives me xi, yi in terms of xy. So I have again a decomposition of height function like this. But of course, these are not minimal surfaces as such with respect to xy. They don't satisfy the minimal surface equation. But if you did a transformation, which you know, phi I is something you know, could be a very nonlinear, highly complicated change, but then you get the height function. So zi xi. So zi xi is minimal with respect to xi. And of course, you can do it for conjugate family and get some nice results. So conjugate family, you know, is where, this is e to the, so it's R naught e to the I theta. And you can fix certain thetas and get a finite sum. And then you can play with it and use it for, yeah, so, okay. But this is the comic thing. There is no surprise in this, because this you can always do, right? Because Z you can always write, this is a trivial fact, that Z you can always write as 1 over Cn, summation m goes from 1 to n Cm, f of xy, where Cn is summation m goes from. So basically all I'm saying is very, very simple. F of xy is summation f of xy n times 1 over n, right? But I just want to weight them, right? Where Cn is summation Cm. 1 over, what is it? Cn is summation Cm. Yeah, of course. So, so this I can always do, but this kind of thing applies in crystallography a lot, because that's what you want to do. Scaled minimal surfaces is what you want to do, and they could be looking like itself, cell similar. So basically, this is, I don't need to write so much, but z of xy is 1 over Cm, Zm Cm minus, and translated. Translation doesn't change the minimality, right? Translation by of, so the minimal surface equation is such that if you scale z, x, y all by c, it again remains minimal. So, and translation of x and y doesn't change anything. So then again you get something like this. This kind of decomposition is possible, which is what they use in crystallography. So cell similar solutions where these are just scaled and translated versions of themselves. And yeah, so that's what I wanted to say. Sorry, very simple talk, and I finished very much. But if you want, I can tell you the proof of that first thing, but it depends how tired you are. This is the end of the. So, okay, so let me show the references. So this talk was based on the following papers of ours. And of course, there are, so this one, interpolation by maximal surfaces, was in functional analysis and in application. These are all in Journal of Ramanujan Journal of Ramanujan Math Society. So there are some many other papers which we referred. And then there are many interesting papers to read in this topic. So I'll just leave it like this. For a few seconds, it's going to be recorded. Okay, so, and another thing I wanted to say was, yeah, so if you want, I can give you that proof. Do you think we should just go through that proof a little, or? Okay, okay. Yeah, it won't take much time. The first proof. Yeah, so I want to invert the Bjorling formula, right? And so the thing is, when I want to invert it, I have to take its differential and try to invert that first and apply inverse function theorem. That's not possible, but you have to restrict. So n is the space of time-like unit normals, and n is L perp to A prime. And so I consider Jn's, which are, delta n, I should have told what is delta n and all that. So let me just write a few things on the board. So dn is integral n cross A prime L, and delta n is A prime, was the one which was E perpendicular to. So d n prime E perpendicular to, A cross, so A prime, yeah. So some geometry and some geometric considerations and analytic considerations gives you these spaces. And in this space, bit by slice by slice, actually we invert it. So H in the equation 3, we want to invert on H inverse on Jn. So H restricted to Xn is Hn, and Hn gamma comma d is A plus I decomposed with gamma, right? So now Tn, how does the tangent space look like? The tangent space looks like all those v comma d in here, such that A prime du real part of this prime is perpendicular to delta n. So it's not there is a condition like this, and S is, so where this was such that S of u0 was 0. So on this particular space, so slice by slice we invert it. This condition comes when you solve the invertibility equation. This has to be there. So then Hn looks like this, and this is a linear combination of A prime d0 n prime, thus Hn Tn contained in Jn. So when we calculate the differential of H, we find that it is actually Hn when restricted to Tn, and then we show it's invertible because it's just a matter of calculation that this is true, that's the geometric condition, and then we can show that it's invertible. And then it's a matter of then applying the inverse function theorem around A plus ID0. X0 is equal to A plus ID0, and finding the neighborhood, so that the inverse function theorem neighborhoods are compatible with these neighborhoods. So there are a lot of things I am not saying because you have to actually find a special ball about x naught. X naught is a special point, and you will be able to find a special ball such that curly J had this different topology, right? V intersection Jn is open in Jn in sup norm topology, then V is open in J, and it's not the so balls you can't find sup norm balls contained in open sets in that, but there will be one particular sup norm ball which will be contained around x naught, which will be contained in this, and then we can prove the interpolation theorem by find the neighborhood. This eta 1 and eta 2 are coming from that ball, and then we can just some calculation to show this. Okay, I'll stop there.
Right, are there any questions? Oh, yeah.
I have a quick question.
Yeah.
Could you go back to the slide where you showed us a Shirk singly periodic surface, and then so you claim that these physicists can actually decompose.
Yes, the height function. Exactly.
So these they actually decompose it as an actual sum of shifted kilovolts.
Yes.
And then
the height functions.
Okay. So
yes. The height function.
I'm allowed to scale as well, right? Or
once again,
I'm allowed to.
No, not the scale one. Exactly. These are exactly honest minimal surfaces.
Okay. So there's going to be a lot of cancellation, right? Because I mean, the helicoid goes out.
Yeah, I don't know. I just saw it on Mathematica that it works. I don't really know how they
can.
Back
to the picture.
Yeah.
Right.
Somewhere this is happening. That.
Oh, I'm sorry.
This continues. Sorry, this is just a part of the surface.
Right. Okay.
Yeah, I think continues like this, then this. Yeah. Of course.
Okay. Yeah. So it's not possible to see. Maybe
what's not possible to see and why it's happening?
Yeah, I mean, like, okay, hard question.
Yeah, Euler-Ramanujan identity is very like God-given. I don't know, other identities may also give us. Like this one also gave us this one. Actually, we are trying to see if there are other identities using certain techniques which will give us exact minimal surfaces on the right-hand side, height functions. Some success, let's see. Yeah. Okay, so yeah, so this is the, once you see this, you don't forget it, right? There are these.
So, okay, so how did these people figure this out?
Once again, sorry.
How did the condensed matter physicists?
So these are screw dislocations, and you array them, actually they array them in a plane. And then they see that, okay, for them it was scaled and translated also. The shark surface they get are actually scaled and translated versions. The actual surface you get, what is that called? In crystallography, that is as a name. Shit, I'm sorry, I don't remember this. But so they actually do it in a whole plane, put the helicoids like that, and when you add it, you get, maybe you can take a look. I didn't put the first, I'm sorry, I didn't put reference to the first one. I put reference to a second paper of his. So decomposition of height functions of Shark's first surface. So this is not the one, sorry, this is not the one which has that. There is another one. Yeah, shifted, and so you put it in a plane, shifted array, and you try to add up the lengths, height functions. You, lo and behold, you get a height function of a minimal surface with scalings. Yeah, so that could be a more general phenomena. That's what we think. Yeah. Okay.
Any other questions? I had a question.
Yeah.
So I was wondering whether it ever made sense to ask about interpolating between more than two curves, or whether that would always be over.
Yeah. That also can be done.
Okay.
Similar, I mean, yeah, then you are also probably even allowing genus and so on.
Oh.
There could be, yeah, that also makes sense. And I have also tried that. Trying that. Yeah.
Oh, no.
Yeah, try not.
Oh, three. Okay.
Right.
Oh.
Right. So
Oh, yeah, I
there's,
think
I guess these are the trinoids. Yeah. Three curves you're interpolating. Yeah. We don't know. Maybe if they're close enough, yes. That's what Douglas says. I mean, Douglas's result says, right?
This guy also exists in genus one. Could put a hand
Yes.
in there. But so how do you control, or you assume something about the genus when you do this connecting of curves?
So far, no genus.
No genus.
Yeah, so far we have not got anything with genus. But yeah, you have to, maybe some topological condition you have to put. Yes. No questions from the students? I thought I made it very elementary.
All right. So if there are no more questions, let's thank Rukmini again for a wonderful talk.
Okay.